Okay, start recording. Okay, so today we're going to finish up chapter 23, right? On the last section, which is actually how we can do some calculations with particles in a charge or in an electric field. And that's going to be our little worksheet for today after I show you guys, talk a little bit about this section and also show you guys an example that's going to be pretty similar to what we have on the worksheet today. Okay, so far we've been doing all these calculations with electric fields, like how do you calculate the electric field for a point source? How do you calculate electric field if you have a stick? How do you calculate electric field if you have a plane? Okay, and if you have a plane and you put them next to each other, put two planes next to each other, two charged planes next to each other, you actually create this thing called capacitor, right? And we found that inside a capacitor, oops, not that one, inside a capacitor, right, you actually have a constant electric field where if you want to calculate the electric field between the two plates inside a capacitor, it's just the charge density divided by epsilon naught. Now hopefully we start seeing why, using 1 over 4 pi epsilon naught is kind of useful versus that k that we had originally, right? Because remember k was 8.8, was it 8? Yeah. 8.987 times 10 to the 9, right? And they'll have coulombs, I think meters squared per charge square. And then we had this 1 over 4 pi epsilon naught thing, right? And you may have thought, it's like, why are we writing all this 1 over 4 pi epsilon thing, right, when k works just as well, right? But now that inside capacitor, instead of having to, if you try to write this in k, right, there's going to be a bunch of 4 pi's around. Now, inside capacitor, that the constant you see in there, right, is just epsilon naught, right? Or epsilon naught is 8.85 times 10 to the negative 12. And it's basically upside down from that. Newtons per coulomb square. And you can see that how, that 4 pi, doesn't stick around that long, okay? It was only in Coulomb's law. So what we're going to do now is we're going to figure out, well, now we can calculate all these different electric fields, right? And an electric field is just a way for us to calculate the electric force on something if there's a positive test charge placed there, right? So imagine you have some electric field, right? Let's go in this way. Call that the electric field, okay? Right, and it has some source. We don't know what the source is. At this point, it doesn't. We don't care that much if we just want to figure out the force, right? If I place a positive charge here, right, that charge is going to feel a force in the same direction as the electric field, called the electric force, right? If there was a negative charge there, right? If the charge happens to be negative, it'll actually go in the opposite direction, right? It'll go opposite direction of the electric field. Right, hopefully that makes sense. And that's because when you want to convert, if you have the electric field and you know the charge, you want to calculate the force, all you have to do is multiply the electric field by the charge. And when I say multiply, basically scaling that vector, right? Because the electric field can have some x component, some y component. Both of those just kind of factors in, okay? Right? And electric field is very useful, such as, the lights in our room, right, is actually working on electric field. So the way that these fluorescent tube works is that the wall socket actually applies an electric field on the two ends of the tube. Actually, I have one here. Right. Yeah. Actually applies an electric field on the two ends of the tube, right? And that accelerates electrons through the tube. As these electrons accelerate through the tube, it bumps into the fluorescent material inside. It's just some chemical, right? And that actually creates light for us. And that's how these little fluorescent tube works. Okay, and I think last time when I had the light off, right, I can create an electric field and actually make this tube light up. Even without connecting it to the wall socket, right? Because it's actually the electric field that's accelerating the electrons, okay? You don't need to actually directly connect it. You know, well, to move cars, if you have an electric car, that also works on the principle of electric field. These doors over here, it also works on the principle of electric field. It's actually actually it's probably a magnetic field that they use. It's probably more efficient. But on the same idea, you can use electric field to basically attract, you know, a piece of charge thing to it, and that allows you to open or close doors. Okay, controls aircrafts, and for scientists like you guys, right? There's, you know, a lot of experiments, right, runs on the fact that we can actually create and control these electric field. And this is an experiment I used to work on, known as LUX, the Large Underground Xenon. So you have a big vat of xenon in here, and the idea is that if you have some particle that comes in, it can actually, you know, crash into the xenon. When it crashes into the xenon, it's just like a car crashing into another car, right? There's to be little pieces of the parts coming out, right? As opposed to little car parts coming out, right? When you crash it two atoms together, right, the electrons come flying out, right? So there's the little pieces of electron that comes flying out. And this experiment is based on the fact that you apply an electric field downward like this, and therefore when that crash happens, you actually accelerate all the electrons upward, and that way you can actually detect it on the top of the detector. Okay, and that's one of the things that is very useful in physics experiments. In fact, you know, this is used to be my student when I was a postdoc. She now works at Waymo for some reason. Perfectly good job. No, it's a good high-paying job, right? She works at Waymo, the little self-driving car that Google does. Anyway, so we worked on together to basically map out these electric field. You can see the little diagram here that we published a few years ago, where these little gray lines are the electric field lines. Okay, so you can see that one of the things we talked about last time is that electric field lines should never cross each other, right? Right? If they cross each other, it's very, very confusing for the electron, right? If you put an electron there, which way does it go, right? They should never cross each other, and you can actually simulate this using this software that we had called COMSOL. And this is not just useful in physics experiments. If you're ever designing electronics, circuit boards or computer processors or computer memory, any of those electronic components, most of the company uses software called COMSOL to simulate the electric field inside those devices, and that way you don't have, you know, devices exploding because there was just too much electric force on a particular charge. Okay. Okay. That's a little blurb about it. We don't have to read through that. Okay. Let's see. The next picture is not showing up because I need to get to the internet. It's actually kind of important. Maybe I can just draw it. If we don't get the internet, you're going to suffer my bad drawing. So hopefully we can get to the internet and then refresh this page. Sync. Picture update. I want to look at this picture. While I'm waiting for the internet to download my pictures for me, any questions so far about how, if you know the electric field of something, it's pretty easy to calculate the electric force, right? You just have to multiply that by the charge, right? There's no epsilon naught, there's no k, you don't have to calculate anything, right? Yeah, question? Oh. Oh, now you're just being mean to me. Okay, I guess you guys get to suffer my terrible drawings then. Okay, so another technology that uses a lot of electric field is actually DNA identification. And what I mean by that, so unfortunately the picture is not there, right? So DNA, so hopefully you guys know what DNA looks like, right? This is double helix thing. Okay, this is my terrible drawing, right? This is what the DNA looks like to me. Okay, so what you can do is actually you can have encoders here that can actually slice off different pieces of it, and the lengths of these things depend on what genes are expressed on these DNAs. Okay, so like, you know, for me, you know, this one might be, you know, a short one, then a long one, and a short one, and we're just kind of estimating this stuff. And how do you identify people with DNA? Okay, once you have this little piece of DNA chopped off, right? Let's do that in green still, even though DNAs are not green, right? Right. This has a certain length, right? Okay, and when you chop these DNA off, what happens is that they develop a certain amount of charge, right? Charge of your DNA. Okay, right? And since this has a certain length, it has a certain number of molecules in it, so you actually also know the mass of that little piece of DNA, right? So you know the charge, you know the mass, okay? So, and this is where the picture is a lot better. Wish I can fix that. Now it's spinning, right? Maybe if I close it and open it again, it'll try to do that. Where the pictures is a lot better. Luckily we're recording all this, right? Anyway, so what happened is that if you put this little piece of DNA, right, in a gel pack, so usually it runs down a column, and you put an electric field in this direction, okay, what happened is that the electric field is going to exert a certain electric force to it equal to the charge times that electric field, right? Right? And that charge is determined by basically which slice of DNA you slice off, okay? And also, right, if you exert a force on something, that's going to create a mass times acceleration, right? A force is actually going to create an acceleration on something depending on what the mass of that object is, okay? So when you're doing DNA identification, you know this piece, right? Because you can set the electric field to be whatever you want, right? And what happened is that this, let's see, let me go back to red, right? The acceleration downward, you can actually measure this by just basically looking at the DNA, right? How far does it go down after like maybe like, you know, 10 minutes or something like that. These DNA kind of moves kind of pretty slow, okay? Okay, so this acceleration, right, is going to be proportional to how far this delta y is, right? How far it moved down. Okay, hopefully that makes sense, right? If you solve this for A, right, you're just going to have the charge divided by the mass times the electric field. Since you know what the electric field is, basically knowing how far your DNA moves along this gel tells you the charge to the mass ratio, which is sort of neat. Oops, let me maximize that. Okay, so you can actually, so like each person's DNA, when you splice it up, right, using these genetic markers, each of our DNA will have different charge to mass ratio per splice. Okay, so one person, you know, may have the same gene, like let's say this is not true, okay, so those of you who know genetics, don't yell at me, right? Let's say like the I don't know, there's some gene that determines, you know, the height of a person, right? Okay, so what you can do is actually, if, you know, my gene, maybe it'll move, you know, 5 centimeters in 10 minutes, where maybe a different person, right, instead of moving 5 centimeters, it'll move like 10 centimeters instead, because that their height gene, whatever that is, right, just have a different charge to mass ratio. Okay, and this is how DNA identification works, by just not just using one genetic fingerprint, but using like, usually they do like a panel of 12, where each person will have a different basically shape to it. And when this picture loads, you can actually see that. Actually, maybe I can just go on. What? Does anyone else have the same amount of trouble with ED-ROM? Yeah, the thing is, like, I think they do something once in a while, and you just have to. It connects for like a month, and it works perfectly fine for a month. Yeah. Yeah, they probably just don't. Anyway, okay, so, but that's the idea of DNA identification. And if you just Google search DNA identification, you can actually see these little gel pack moving around. And I actually do need the next picture to do the example, okay? So that's going to be a problem if we don't have that. That I can just connect through the hard wire. You said they show a new certificate this morning? Okay. So we're on this side. Let me pause it. Okay. Okay, so anyway, so you can slice and dice, people's DNA up, and for each person, for particular sets of genes, it would have a different length. Let's do that in green, right? And each of these different lengths will have a different mass, right? The longer the molecule, the heavier it is, and also have a different amount of charge on it. So what you do is you take someone's DNA, you slice it up into like, multiple pieces, and you insert it into these little gel packs. Or now I need to use red, right? And all the little DNA molecule kind of starts off up here on top, and then you apply an electric field downward on it. And of course, the color is horrible. Let's just stay with red. Nope. Stay with red. Okay. And what happened is that depending on the mass and the charge ratio of each of the DNA molecules, these DNA will move down at a different time. Okay, different amount of time. Okay. So you can actually, so for me, maybe my DNA are moved down this far, right? But maybe for Cole's DNA, his might be moving down like this. So you can actually use this to identify a person's DNA, and that's how they actually do DNA identification on people. Okay. So, and this is due to the fact that when you have an electric field, and you have a charged particle, right? They're going to have a force on it. And the way you calculate this force is that, well, I have some electric field here. If I place a charge inside that electric field, right, it's going to have an electric force on it. And the simple calculation for that, right, is just charge times the electric field, right? And the sign of the charge is very important, right? Because if this was negative, it will actually point in the opposite direction of the electric field, right? That negative sign does that for you, okay? Now that you can calculate force, right? If you can calculate force, that's going to be, right? Let's go to the left-hand side here, right? That will allow you to also calculate the mass times acceleration of that particular object. So if you know the mass, you know the charge, you know the electric field, you can actually calculate exactly what the acceleration is. And now if you can calculate what acceleration is, we're going to jump back to Chapter 4. I think this was actually chapter. Where was this? When we first covered kinematic equations, I think chapter. Sorry.
Chapter 5.
I think chapter 5 was forces already. Yeah, it's either chapter 4 or chapter 3 or 2. Okay, so for those of you who had the open stacks book, this was chapter 2 and 3 when we did kinematic equations, right? Where if you have the acceleration of an object, right, you can actually calculate how much time, relate the time to the initial velocity of that object, right, to the position of that object, okay? And similarly, if you have acceleration in the y direction, so this is in the x, if you have acceleration in the y direction, right, that will allow you to calculate the position, the amount of time it takes to travel in the y direction, and you can also relate these to the velocity variables, right? So you can actually determine how fast that object is moving, okay? I'm going to try to do an example of this and give you guys more time to work on the worksheet today, where these things called cathode ray tubes. These are like old televisions. You might have seen one of these. It's just, you know, maybe in a museum somewhere. That's what this is usually inside a box, right, to keep people from touching it. But a cathode ray tube is basically based on having this base where you have electrons that fly through the system, okay? Basically a similar way that the electrons are flying through these fluorescent tubes here, right? But instead of allowing them to go in a straight line, you have a capacitor plate here that creates an electric field downward here, okay? And since the electric field is downward, the charge is negative, it's going to get accelerated upward, right? And that actually allows you to steer the electrons into onto a screen where wherever the electrons are hitting, that's where the screen lights up, right? And if it happens to be like a little red phosphorus pixel here, it will light up red. If it's blue, it will light up blue. So you can actually produce all the colors here. Like, but you know, this is I feel like I'm like talking. This is where I feel old, right? Because I've actually seen these things in my life, where I think you guys is all on LCDs, right? But the principle of this is kind of cool. Actually, when I was a kid, I always take these things apart because they're like you can get some free magnets out of it. Anyway, so what we can do is you can actually calculate exactly where horizontally it's going to hit the screen if you know the electric field in here, right? And also the length of this thing called the deflecting plate. It's basically deflecting that electron up and down, okay? So let's say we have an electron gun that fires into a deflecting plate, okay? And that electron is going pretty fast, 1,000,000 meters per second, okay? 10 to the 6. And this deflecting plate has a length, so this is the horizontal direction, of 2 centimeters, okay? Be careful on your worksheet. The worksheet actually has gives you the vertical dimension, not the horizontal, okay? And the electric field strength is, let's say, 1,000 newtons per coulomb, and it's going downward, okay? And we want to calculate how far up the screen is that electron going to hit the screen, okay? If this screen happens to be 10 centimeters away, okay? So let's redo this drawing. So let's do the setup of the problem, okay? I'm going to simplify that drawing quite a bit so that I can actually understand it. So you have these deflecting plates, okay? Right? And since the electric field points downward, I actually know the charge on these deflecting plates also, right? So that's the electric field going downward, okay? And we'll have a little electron, let's see, flying in the middle of it straight through, right? So the initial velocity of that electron is actually 1.0 times 10 to the 6 meters per second in the I hat direction, okay? And for me to declare these things called I hat and J hats, right, I have to tell you what the coordinate system I'm using is, right? So horizontal is X, vertical is Y, okay? So, and the screen, the plate has a length of 2 centimeters, and then the distance to the screen is actually 10 centimeters, is longer, right? So let me draw the screen up here, okay? So the electron actually has to travel 2 centimeters and 10 centimeters in the X direction, right? The problem is that while it is inside the electric field, it is have a constant acceleration to it, right? Because the electric force is going to pull it upward, okay? Outside the deflecting plate, it's going to go in a straight line, right? So the important thing is that here, right, we have to solve a problem with constant acceleration, right? But here we have acceleration is equal to 0. I mean, technically it's constant, but we have no acceleration, right? So let's figure out what that acceleration is in the first place, right? Acceleration, right, is the force, in this case just the electric force divided by the mass, okay? The electric force, right, is just the charge of the electron times the electric field, right, and this is mass of the electron, okay? Let's just figure out the magnitude of everything, and we know that the acceleration is going to be upward, right? So we know it's going to be in the positive j hat direction. So the charge of an electron is negative 1.6 times 10 to the negative 19 coulomb. The electric field we're dealing with is 1,000 newtons per coulomb, right? And the mass of an electron, this I may not know off the top of my head. Who knows that? Who knows it off the top of their head? It's 10 to the negative 31. But of electron. Yeah, 9.1. That's the problem. 10 to the negative 31. It's pretty light in kilograms. Okay. Right? And you check all this stuff in. We just care about the magnitude. Okay. Okay. 1.6. 10 to the negative 19. I can't type. 10 times 1,000 divided by 9.1 times 10 to the negative 31. Okay, so this acceleration is huge. 1.3, sorry, 1.7. I'm going to round to 3 sig figs. So I'm keeping one more sig figs than we need because I know the problem is going to be 2 sig figs. Times 10 to the 14 meters per second square. It's a huge acceleration, but it's only going to experience that for a very short amount of time. Okay, so to figure out, right, the path of this little electron, right, it's going to start off here. It's going to get accelerated, right? I'm not drawing the acceleration very well. In the when it's inside the electric field, but then once it exits the electric field, it's just going to go in a straight line, right? Because there's no more forces acting on it. Okay, so this is the curved part, right? This is the straight part. So let's deal with the curved part first. Okay, in the curved part, curved, right? We have a constant acceleration. The acceleration is that. Okay, and we have to determine where is this, how far up the, what is this delta y, right? So y final minus y equals to y initial plus vi y times delta t plus 1/2 acceleration in the y direction delta t squared. So that's one of the kinematic equations we just saw above. Okay, y initial, right, if we set our axis here, it's going to be 0, right? The initial velocity of the object is also 0, right, because we had no initial velocity. Okay, so y final is actually just this number. Okay, so I can punch that in, times 0.5. Well, I don't know what delta t is. That's the problem, right? Okay, so how do I find delta t? Delta t, right, is the amount of time that the electron is going to spend inside between the two plates, right? So we know the initial velocity of the electron, right? Right. So distance x final, x initial plus vi x delta t, right? So we can actually solve this for delta t, and delta t is, because x initial is also 0 because we started off at 0, 0. So delta t is going to be xf over v not initial, right? And xf was 2 centimeters, so 0.02. I'm gonna skip the units because we're going to be using all SI units, and then divide it by 1 million meters per second. Okay. Okay. So that's going to be 0.02 times 10 to the negative 6 seconds. In other words, I moved the decimal over twice. It's 2.0 times 10 to the negative 8 seconds. Okay. So that's what delta t is. Okay. Whew. Okay. So if we can punch that in, my acceleration is huge, times 1/2 times 2 times 10 to the negative 8 squared, right? Okay. XF is actually going to be 3.52 times 10 to the negative 2 meters, okay? So by the time it exits the deflecting plate, it's going to move up about 3.5 centimeters, okay? Right? But the problem is not done yet, because right now we have to, that just gets us to here, right? We have to figure out how far up it's going to go, right? Traveling across that 10 centimeter gap, okay? So on the straight part, okay, we have acceleration is actually 0 there, right? Because it's just moving in the little tube there, okay? So therefore, right, y final is going to be equal y initial plus VI y delta t plus 1/2 AY delta t squared. Okay, so this delta t is different, right? So be careful these variables don't connect to each other. Okay, right? Since acceleration is 0 there, this whole term in the back is 0. Okay, that's nice, right? What is V initial? You guys want to? Anyone wants to venture a guess? Is it 0 or not 0? It's not 0 anymore, right? Because now it's going in a vertical direction also. Okay, so we have to calculate V initial and delta t, right? Because y initial here is actually y final from the previous part, right? Okay, so V initial, right, is just the amount of time it got accelerated, 2.0 times 10 to the negative 8 seconds, and the acceleration was some big number, right? 1.76 times 10 to the 14 meters per second square. Multiply those two numbers together, times 1.76 e to the 14. Okay, so it's zipping around pretty fast in the y direction also. So that's checked. We have to figure out how much time, right, this particle is going to spend to travel that 10 centimeters, right? We can use the same technique we have before here. Instead of 2 centimeters, delta t in the straight part is going to be 10 times 10 to the negative 8 seconds. In other words, 10 to the minus 7 seconds. Okay, so now we have this piece, we have this piece. We can solve for y final. So y final is where the screen disappears. There it goes. Y final, right, is y initial, 3.52 times 10 to the minus 2, right, plus V initial, which is 3.52 times 10 to the 6. And then the amount of time it spends in there is 10 to the negative 7 seconds. Okay, this is meters per second. Okay, so you add these guys up. So this should actually cancel out to make this negative 1. Okay, wait. This is funny. These numbers are almost the same. These numbers are exactly the same. Okay, anyway, 3.52, 10 to the negative 2, plus 3.52, 10 to the negative 1, right? Right, because this is 7, this is 6, so it should multiply together to be 10 to the negative 1. So this turns out to be 3.87 times 10 to the negative 1 meter. Or another word, I'm going to round this to 2 sig figs, right? 3.39 centimeters. Okay. Actually, just answer it in SI units. It's fine. 0.39 meters. Okay. So that's how far it'll get deflected up. Okay. So, as usual with my struggle with the internet today,